Okay, so we're gonna start off learning module number 4, which has to do with magnetism. Magnetism and electromagnetism. So we're going to be starting to talk about phenomenon that has to do with magnetism. We're going to see that this phenomenon, whenever we have charges in movement, which is basically whenever we create an electrical current, we're automatically going to be generating magnetic fields. And magnetic fields can be generated naturally or by natural phenomena, or it can be induced or generated artificially. And that's basically what we call electromagnetism. So the first thing we're going to be, the first things we're going to be seeing have to do with concepts that we need to be familiar with. And one of the things that this topic has is that there's a bunch of laws. There's a bunch of laws that have to do with a bunch of people and a bunch of scientists that develop these laws explaining some of the phenomena. So similar to Ohm's law, and then we, yes.
What is the name of the topic?
That's
model
4. The learning module is magnetism and electromagnetism. And so the concept of magnetism, this isn't I know that this isn't a new concept for any of you, because I think we're all familiar with magnets. Yes. How would you describe a magnet? You know magnets. You surely interacted with them. Everybody knows magnets. If my 6-year-old daughter came up to you and said, "Can you tell me what a magnet is?" How would you define a magnet?
In hindsight, I would just say it's like a piece of metal that attracts or repels certain.
We're so smart.
Yeah, it's gonna. I'm gonna refine that answer a little bit. You mentioned that it's a metal. Let's say that it's something, because it can be a metal. It's a certain type of material, but we can also create magnets with other things. It's something that is going to create a phenomenon where it repels or attracts other things. And basically that's the phenomenon of magnetism. And the phenomenon of magnetism, we can see it all around us. The Earth itself is an object that's magnetized. The Earth has poles, right? We know there's a North Pole and there's a South Pole. We know that there are the cardinal points, north, south, east, west, and those have to do with a certain magnetic effect or polarity that our Earth has as an object. And so basically, magnetism is going to be this phenomenon that has to do with certain types of materials or objects where a magnetic field is created. And this whenever we say the word field, like when we were talking about an electrical field, whenever we say that, we're talking about something invisible. We're talking about something invisible, something we can't see, that whenever we interact with that something or that field, there's always going to be forces generated. So when we were talking about an electrical field, we had an electrical charge and there was a field around it. So it's this thing that we can't see. If we put another electrical charge in the field, the force is generated. The same thing happens with the concept of a magnetic field. A magnetic field is going to be this invisible thing that's around an object or a material, that when other objects or materials interact with it, forces are going to be generated. Now, there's a difference between an electrical and a magnetic field. A magnetic field is always going to be generated with regards to two poles or two references. When we talk about magnets, or even when we talk about the Earth, again, we know that there's a north and a south, right? There's always a north and a south. With a magnet or a magnetic phenomenon, there's always going to be two poles. There's always going to be two poles. That's important because when we're talking about electrical field, I can have just one electrical charge that's generating an electrical field. The charge can be positive or negative, but I can have just one thing generating an electrical field. In the case of a magnet or a magnetic phenomenon, there's always going to be two things that are related. There's always going to be two poles. And these two poles are always going to be opposite each other. They're always going to be opposite, or they're always going to be opposing each other. And so, like the images that we have there, those are different configurations of magnets. We're going to be talking about some of them in a little while. But let's look at the last one, which is the Earth. So we're looking at the Earth as a ball, and it has two poles, the North Pole and the South Pole. So basically, there's a field that's being generated where there are lines that are going from the north to the south, from the north to the south. Okay, you see those lines that are coming out of the Earth, and these are imaginary lines. Yes. They're always going from one pole to the other. And we're imagining that they're going they're going out of the north and coming into the south. Okay, it's always going to be that connection. We can't have a magnet with just one pole. It doesn't make sense. We always have to have two poles.
And it doesn't matter where it comes from.
No, the up or down is just kind of a reference because we always think of north as up and south as down, but in reality, it's like Australians are looking the other way around, right? Because they're on the bottom of the Earth, and it's not that. It's just a reference. Okay. So no, it really doesn't matter how they're oriented. It's just a reference that we call them north and south. And actually, the poles of a magnet are called north and south because with regards to the Earth, you know that a compass is a magnet, and a compass is always going to point north, and it's because it's being oriented with regards to the north pole of the Earth, and that's why we reference it. The picture that's before the Earth, the fourth picture, is what's called a bar magnet, which is basically just a block, a rectangular block, and it's got a north and a south. And again, the magnetism or the flow of magnetism is going from north to south. Now, the third, now I'm going to start the other way around. I'm going to talk about the first image. In the first image we have there, it's just a wire. It's just a piece of wire. But in that piece of wire, there's a current going through. And these scientists, many years ago, that didn't have Netflix, they didn't have streaming services, they weren't expecting the new Doctor Strange movie. They had a lot of free time on their hands. So instead of doing all the things we do, they did experiments because they had a lot of free time. So there's a bunch of people there, Faraday, Lenz, Hall, etc., did a bunch of Ampere, that did a bunch of experiments. So one of these guys said, okay, I have a cable, a wire, and I put some current through it. And if I grab a piece of metal and put it close to the wire, suddenly funk, there's a magnetic field. But if there's no current going through it, there's no magnetic field. So what's happening? And what they discovered is that if I have any conductor where I put an electrical current going through it, meaning any conductor where there's movement of electrons, there's automatically going to be a magnetic field around it. Anytime I have current moving through something, there's going to be a magnetic field automatically. I don't know if you guys ever did this experiment when you were in high school, secondary school, or whatever, where you can grab a pencil or a pen or whatever and just wrap a cable around it and just connect it to a battery, and suddenly you've got a magnet. What's creating the magnet is the movement of electrons. The movement of electrons generates the magnet. So any wire that has a current going through it generates a magnet. Notice that there's a hand there doing a thumbs up. There's a reason for that, and you guys are going to be doing a lot of this during the next few topics. There are hand rules that have to do with if the magnetic field is going one way and the current is going another way, the force is going this way. So there's a bunch of rules that are called the right hand rule. That, and if you're left-handed, then there's trouble. The right hand rule, the right hand is going to tell you based on a magnetic field, the current and forces. The right hand rule is going to tell you where everything is going, depending on how your fingers are pointing. And so if I have a wire, and that wire, if I put current through it, I can generate a magnetic field. If I configure that wire in different ways, I can generate different applications of the magnetic field. Okay, which is interesting. So for example, well, applications of this, or what can be applications of these wires and things, a bunch of things that you've interacted with. I'm going to start with something I like in particular, but if you're into music, an electric guitar, the way an electric guitar works is that if you look at an electric guitar, there's the strings and there's these things here on this side that are called pickups. And if you look at them, there's 6 little metal circles that are aligned with the strings. Basically, what's happening is that those little metal things are magnets. And the magnet, imagine that the magnetic field is kind of like something invisible, that if you move it, there is a reaction. There's a reaction. And so these are magnets that are generating a magnetic field. If I have a string on top of it, if I move the string, the magnetic field, which was static, the moment I move the string, it's like I'm moving the magnetic field. And the magnetic field is going to move at the same frequency as the current. And that is captured, and that is what is sent to the audio. Well, that's an application I like a lot because I like music and I like guitars. But a more simple application that you guys have interacted with, and that's that third image here, which is called a solenoid. What is basically a solenoid? In that third image, there is, you might not be able to see it, but there's a core. There's a, let's say that there's a metal cylinder in the middle. And around it, it's just wire that's wrapped around it. It's not touching it, it's just kind of wrapped around. Well, if there's no electrical current going through that wire, there's no magnetic field. But if I put a current through the wire, a magnetic field is going to be generated. What would happen to a metal thing that's inside a magnetic field if suddenly I put a magnetic field on it? Let's say that I have, let's say that you have a piece of metal.
Yes.
There's nothing around it. And suddenly I put a magnetic field next to that piece of metal. What do you think would happen to that piece of metal? It would move.
Yes.
Simply move. Okay. The piece of metal is static. The moment I put a magnetic field close to it, it's either going to be repelled or attracted, right? So it's going to move. So if I have a little piece of metal here in the middle and I put an electric current through it, this piece of metal is going to want to move somewhere. Either it might want to move up or might want to move down. Can anybody identify what an application of that could be? And I think most of you have used it in houses or in. Do any of you have electrical locks in your houses or somewhere? Those magnetic locks that you have to push a button and something opens? You've never seen. Come on, you've never seen a magnetic lock. Oh, but you've seen or you've interacted with magnetic locks.
The one for the hotels?
Yeah, for example, you go someplace and the door is locked and you have to push a button.
La puerta aquí de la oficina.
This one here, for example, that's what's inside there is this. There's the lock, and the moment it can work either way. So the moment I press the button, I'm either disconnecting the magnetic field or I'm connecting it, and it's making a metal bar move. Okay, so the magnetic fields can be extremely strong. So the moment you activate a magnetic field, that movement or that stoppage is going to be really, really strong. The moment you remove it, there's no force and there's a spring that makes it come back. So a solenoid, which is this configuration where we have a core and we have something wrapped around it, solenoids are used for piston movements, and they're usually used for these sorts of applications like magnetic locks that you surely interacted with.
What about
Teacher,
Motors as well, yes.
I'm not asleep, but my eyes hurt. No, I think I
I'm-
put contacts, in.
I'm not hungry, but my stomach
Good night. Yeah.
is.
I'm guessing.
So these are just some
What
examples.
about an MRI scan?
Okay, MRIs, definitely. Believe me, I know about MRIs and PET scans. An MRI and a PET scan, and we're actually we can talk a little bit about this, but these are used, basically what an MRI does, and I don't know if any of you have had MRIs, but an MRI is a magnetic resonance, imaging. One of the things about electromagnetic phenomena is, and I love the way my friend from Switzerland explained this to me, because when I was over there in Switzerland, we were working on projects that have to do with optics and electromagnetic phenomenon. Is that a cool thing of seeing is that electromagnetic phenomenons in the electromagnetic spectrum, for some electromagnetic waveforms or wavelengths, things are invisible to them. So what does this mean? Things are invisible and things react differently. So basically what a magnetic resonance imaging machine does is that it's generating a very strong magnetic field that's going through your body. And the bounce off of that through certain parts of your body reacts differently and can be able to detect different layers in your body. Okay. If any of you have been in a MRI machine with tomography, basically, it's loud. Tomography. So there's two types of tomography. There's the simple one and there's the contrasted one. The contrasted one. Yeah, you feel hot and you have a taste here automatically. The contrasting version of the tomography or the MRI, the thing that they inject you, and that's also used in a PET scan. The thing that they inject you is just to be able for certain things to be more to glow exactly in your body when they're doing the magnetic resonance. The contrasting element is going to make certain things come out. And so if any of you have been in those machines, they are by default extremely loud. The machine is kind of like a semicircle. That semicircle where you're put into is literally this coil that I just mentioned. It's the same coil, but it's a huge set of coils that are in a round form. A solenoid can be either vertical or it can be round. And it's basically generating these magnetic fields that are going through your body. The sounds that you hear in an MRI that are really, really loud is that, and by the way, you know that MRIs are expensive. One of the reasons they're expensive is I just said, and I repeated, that we need electrical current to create a magnet. One of the laws that we're going to see that's very simple. The stronger the current, the stronger the magnet. Simple as that. The stronger the current, the stronger the magnet. We need a lot of current to create a magnet strong enough to be able to send, to be able to do MRI scanning. So there's a lot of power involved. So that's one of the main reasons these things are expensive. They're expensive because they need a lot of energy.
That is why it's famous to do a lot. You can be
It's MRIs, the PET scans, the idea is for you to have them when you need them. You shouldn't be doing, it's like an X-ray. An X-ray, when they do an X-ray, it's minimum the amount of X-rays that are going through your body, but if you have an X-ray every day, well,
Like
that's
the person
different.
that's working there.
Yeah, I always find it funny in the X-rays, it's like, don't worry, everything's gonna be fine. Take the X-ray, and then the patient goes. Battens down the shelf, and it's like, okay, the X-ray, and you're like, but why are you over there? But there's a reason for that. The person that's doing the X-rays is exposed every day to the X-rays. That's why they need to be protected. If you're doing an X-ray, you do an X-ray once every year or something like that, it's not going to affect you. If you're doing them that's why for cancer, they use radiotherapy because it's very aggressive that every day they're attacking the cancer that way. But the other reason why it's loud, I don't know, coming back to the example of the magnetic lock. If you ever use the magnetic lock, you notice that when you press the button, you can hear the buzz.
Yes.
You hear the buzz. Now, when you use a magnetic lock, you can literally hear the buzz. Now, the amount of current you need for a magnetic lock is minimal. Now imagine the amount of current you need for a machine that's half the size of this room. So when you're inside an MRI, and those of you who have been inside it, it's kind of like you're in a rave party with dubstep music. You're inside, it's like those sounds are literally the coil being energized and de-energized. It's the same as when you press the magnetic lock, but it's a huge magnetic coil that's being generated. But the MRI is a very good example of that, and that's why they're really, really loud. I was I was at a conference, and the person who was giving the conference was talking about something that was called robust design and how we design things. And if you have ever been in an MRI machine, if you're claustrophobic, that can be something very, very they ask you, of course.
They tell you do not breathe.
Yeah, but if you're an adult, you have certain coping mechanisms for that. But now imagine if you're a child and you have to be put in an MRI machine. And so this person was talking about design and how we approach design, and they were talking about these MRI machines, where actually the MRI machine is the whole MRI machine is a pirate ship. The whole a pirate ship, like a pirate ship, where it's I don't know, it's colored with Disney stuff, and there's a screen where you can watch movies. So when the child goes in, it's a little bit less traumatic because the experience itself can be claustrophobic. But if you've ever been in one, the sounds can be really, really, really stressful. And
it's not the tomography, another one that's where
they put some earmuffs on. It must be some sort of other version of an maybe not an MRI. I haven't had that experience yet. The other thing is that certain tomographies have to do with certain parts of your body. I think that when the tomography or the PET scan has to do with your head, it's a little bit different, and they put other things there, but that's where it comes from. So the takeaway here is that, again, it's a huge magnet, it's a huge coil, and the sounds are because the coil is being activated, and that activation requires a lot of energy to do it. And so, and the contrasting element. The other is a PET scan. I just had to have a PET scan done. That's different. That's done with it's kind of like an MRI, but it's done with photons. That's different. And they inject you with something as well there, but that's kind of funny because you're radioactive for about 8 hours. So literally you're radioactive. They inject you with something, and you shouldn't be around people for 8 hours because you're radioactive. Because it's a radioactive element that they
which one is that?
the PET they've done all of them to me. The PET scan is the one where it's also it's very similar to an MRI, but it's used to detect other things. And for that one, the contrasting element is necessary, but the contrasting element is radioactive because certain parts of your body react differently to the radioactive material. and they inject you with a radioactive material, and you're radioactive for a few hours after
And the
that.
machine is like the same.
Actually, the machine is literally the same. It's literally the same. It's a semicircle. They put you on the table. They put you in. It doesn't. It isn't as loud. That's one thing I noticed. It isn't as loud as the other machines, but the machine is basically the same. It's very similar. You want to ask?
What can you react to if you do that and then you're around an element?
No, I don't know. The only thing they tell you is that you shouldn't be close. You should avoid crowded places. You should avoid.
Having people.
No, women that are
Pregnant.
that are pregnant and children. That's the only thing they tell you to avoid. And you have to flush 3 times every time you go to the bathroom. That's the only thing.
Oh, because your waste becomes radioactive?
No, your pee is radioactive.
Oh.
Literally.
And
That's
what
where
happens to
the
your
agent
cell phone?
goes. That's where the agent goes.
Does something happen to electronics around radioactive things or people?
Like they explode?
No, well, depending on the levels of radiation, electronics could be affected. I don't think for a PET scan or anything like that, electronic equipment isn't something that they mentioned that you should be careful with. It's mostly people. Yeah, it's mostly people, so no. Yeah, you can go home. The only thing that they recommend is for you to be isolated for about 8 hours from, again, children and people who are pregnant. That's the recommendation. And I've been told, but I'm not sure if this is true, that if you go through the procedure and you're in your car, you should try not to go through across the border in that car very recently, because the car is going to be a little bit radioactive. I don't know if this is true. They told me that a person who did this once tried to cross, and they sent them to second review, and the machine detected that something was wrong, and it's because the car was a little bit radioactive after that. So things you get to know about that you didn't know you were going to get to know about. And so life happens. So magnetism. Magnetism is a phenomenon that occurs naturally, that occurs in nature. So there are materials that have magnetic cores. So magnets can be found in nature. The one of them is called magnetite, which is basically a natural magnetic material that can be found on Earth. This is what's usually called iron oxide. The other one is called a lodestone or a leading stone, and that's because again, think about the Middle Ages. Think about these people that people thought were wizards. Again, somebody, because again, they didn't have much to do, saw that if they put a rock in a piece of water and turned the rock, suddenly the rock moved to a certain place, and then they moved the rock, and then they moved, and it's basically a magnet. We know that a magnet is always going to orient itself towards the North Pole. So that's why they were called lodestones, or leading stones. It's basically they discovered, oh, if I get this material is always going to orient me towards a certain place. And these are these natural magnetic phenomena that occur in nature. Now, obviously, magnets are used for a lot of things, like the examples that I just gave you. But looking for these materials to do these applications, I'm going to do a magnetic lock. So let's go find a lodestone deposit where I can make 2,000 locks a day. Well, that's not practical. Okay. So using these materials from nature is not practical. But there's ways in which we can create a magnet artificially, which is basically the electromagnetic phenomenon that we've been talking about. So basically a magnet, the way we represent it generally is that we're going to have these 2 poles that we're going to call north and south. That's what they're called. So we don't say positive and negative. We don't say, we use them as north and south. When we talk about magnetic fields, we don't talk about like in electrical charges or in electric currents. We don't talk about positive and negative. We talk about north and south when we talk about the poles of a magnet. And the magnetic fields are going to be these imaginary lines that are always going to be going from north to south, always going to be going from north to south. They always connected to each other. The density of these lines, the density of the line, meaning how many lines I have in a certain space, is kind of an indication as to how strong the magnetic field is. One thing that we can say that's, what did we say about electrical fields? How is the electrical field, if I'm close to the charge, is the electrical field larger or smaller? If I'm close to the charge, the electrical field is larger. If I step away from the charge or I'm further away from the charge, the electrical field diminishes. The same thing happens with the magnetic field. The closer I am to the object, the stronger the magnetic field is going to be. The further away I am from the object, the weaker it's going to be. And again, magnetic fields are really, really strong for certain objects that are magnetized. I don't know if any of you have tried to join together two opposing poles of a magnet. It's not easy. It's difficult to do. The same thing if I have two magnets and they're connected and I'm trying to separate them, you need a certain amount of force to do that. So magnetic fields can be really, really strong. And a concept here that has to do, that's important, is this density of the magnetic field, which has to do with how many lines are going through a certain particular area. They're always going to be going from north to south. There's some, I've sprinkled this material with a bunch of videos that besides the material that we're seeing here and that's being recorded, there's these videos that are sprinkled around the topics that kind of help reinforce some of them. So, oh, wait, give me a moment. I'm just going to put it here on the screen.
¿Y a ti qué te
Detallito.
But I think the worst thing about, at least for me, for the MRIs and the PET scans and any sort of procedure, at least what I hate is the fasting that you can't eat for 8 hours or before that. That is, but I mean, 2 weeks ago, I mean, 2 or 3 weeks, no, 2 weeks ago, I mean, the weekend was like, I'm gonna eat everything I want to eat on the weekend because on Thursday I had a procedure that required fasting for 8 hours. So on Thursday I couldn't eat. And then on Friday, the PET scan procedure, the thing about the PET scan procedure, it's not kind of like a normal fasting. They give you a diet and it's like, you can't have any sugar. Because when they do a PET scan, the sugar is part of the elements that react in your body. So if you have a lot of sugar, there's going to be parts of your body that are going to come out in the PET scan that are going to be for that. So you can't have any sugar. You can't have any good things to eat, even before the 8 hours of fasting. And that's really, really terrible if you like to eat. Really, really not cool if you like to eat.
It's fine, right?
I think it's number 5 now. Okay, I'm gonna jump over to the.
Teacher, that's why I had to miss one class because my dog had to fast for 8 hours.
Your dog had to fast?
Yes, and me daba lástima que no comiera por más horas de las que.
You needed to feed him, yeah.
Yeah, so I had to miss class.
O sea, pues que le van a operar a las 9 de la mañana. Pero pues imagínate, o sea,
De tanta hambre que tenía.
a las 10 fue lo que más quería comer. Ya dije, ya, me levanto, quiero dormir. Y en la mañana nomás voy que
Well, yeah, I mean, the instinct.
empezó, porque le dije un plato fuera y le empecé a escuchar que lo empezaba a mover. Como que yo ni me empezó a mover.
Ah, sí, la vida también.
Entonces.
Yeah, because after you've done a fasting, I mean, when I did the PET scan, it was I think about 12 hours, and they give you a little bag with a sandwich. I'm not very much of a fan of sandwiches, and even more if they're like vegetarian sandwiches with just lettuce, tomato, and a piece of cheese. but they gave me that. That was the most wonderful sandwich I've had in my life. I was like,
Maybe you liked it
after the maybe, but that was the most wonderful sandwich I've had. It was like, when you're hungry, you're hungry. Let's.
InDriver, descarga la aplicación.
I don't know why the audio is so low, but yeah.
I think we should explore a few solutions.
Grammarly's suggestions catch when your tone might undermine your message.
This is an experiment. I don't know if any of you did this in at some point. Actually, you might be able to do this in the manufacturing, if you have any sort of shadings. If you have a magnet and you just put metal shadings around it, the metal shadings are going to automatically draw the magnetic. When I say metal shadings, it's like kind of rebaba from any sort of solid material. But you have the magnets, you just sprinkle it on, and the magnetic field is going to automatically appear because they're going to be aligned to the magnetic field. And I think that should just be very fine metal shadings that you can use. That's just the example that if we have a wire and we'll put a current through it, the wire is going to automatically so the only thing that's being done there is through the wire, we're just connecting the battery, and there's going to be a current going through the wire. You shouldn't. In the case of this wire, the voltage is very, very small. I think you set it with 1 volt or something like that. Nothing would happen. The only thing that's happening there is that when I have a wire, I'm looking at the magnetic field through the core, and it's going to generate sort of like a concentric circle that represents the wire. And that's an example of a solenoid, which is basically the wire, but it's coiled around something. Same, there's voltage being applied there. The solenoid, because it has a battery in it, is generating the magnetic field, and so we see that there are lines connected through it. So these experiments kind of it's a too loud. Yeah. Too loud. Okay. And so this is the obvious relationship that we already know. So the opposites attract, the same repel, and that's what we're going to see with the magnetic field. So basically, what's happening is that if we have we have the magnetic fields or these imaginary magnetic fields, similar to how we were talking about electrical fields, where the lines of the electrical fields kind of either coincided or aligned or crashed into each other. The same thing is going to happen with the magnetic field. If we have a magnetic field of two opposing poles, the magnetic field lines are going to align and one is going to connect to the other, and that's going to generate that attraction. If we have two magnetic fields from two poles that are the same, the magnetic field lines are going to crash like we see in the second image, and that interaction is going to generate the opposition or that repulsion force that's being generated. Okay.
Ya no es lo-
El cubrebocas, pero se me cayó o sea, tomé agua y se me fue. Entonces, o sea, sí lo que
Okay, so a few other concepts we need to talk about. So magnetic flux. So whenever we talk about flux, and we already talked about electrical flux, flux is basically going to be this reference that has to do with the strength of a field. And basically the flux is going to be the amount of field lines that are going to be going to a certain surface. And so a field or the strength of a field is defined by the flux, and also a flux is related to a field. So we know we already talked about it with regards to electrical field. Now we're going to be referencing it with regards to magnetic fields. So it's going to be the number of magnetic field lines that go through a given closed surface. Magnetic flux is usually represented by a phi, which is the Greek letter. Oh, and by the way, for some reason, I'm not sure what, but whenever we're referencing magnetic fields, we're going to use a B, an uppercase B, like we see here. So uppercase B is we're gonna relate that whenever we see an uppercase B, we're talking about a magnetic field. So phi B is going to be the electrical flux corresponding to a magnetic field. Yes. We also used it, that's a good observation, and we also used it for electrical flux, just that we called it, I think phi E or just phi. So that's a good observation, and usually the phi symbol is used in physics to represent some sort of flux. So the phi that we used before was for electrical flux. Now it's phi B for magnetic flux. There's a lot of Greek symbols that are usually used for. So, for example, usually rho is sometimes used for certain volumetric elements. Sigma is used for certain superficial things. So certain Greek letters are used for different things. Did you guys, I don't think, did any of you have a course in high school called Greco-Latin etymology? No, when I was, I think I mentioned this before, but I remember things from my youth that are totally random, that are completely useless in life, but I remember them. So again, I remember how to sing the national anthem because there was a contest when I was in school and they taught us how to sing it and why, and I don't know why I remember that whenever I sing the national anthem, but it's not something very useful in life. But in high school, I'm not going to say I know how to read Greek, But in high school, there was a course when I was in high school in the 80s that was called Greco-Latin etymology, where the whole course was for us to learn Greek and Latin terminology in high school. It's cool now. So now I look back and I'm like, oh yeah, I know how in Caballeros del Zodiaco where they write Atenea, I know it says Atenea even though it's written in Greek because of that, but that's completely useless. So right now it's cool, but when you're taking it in high school and you're cramming for an exam where you're learning the Greek alphabet and knowing that things I remember, for example, you know, right now you guys know about Marvel, and you know that Thanos, but Thanos, I think they named him Thanos because Thanatos in Greek means death. Thanatos means death. The study of death in psychology is called thanatology. So those things, that's completely useless, but Thanos, oh yeah, that's because of death, because I took this course in high school. So there's a bunch of words that come from Greek and Latin, and I think actually there were 2 courses. There wasn't even one, there was 2 courses of that. They combined both of them, but we had to learn the symbols and all that. So the magnetic flux formula is exactly the same as the electrical flux formula that we've seen before. It's actually exactly the same concept. Electrical flux is going to be equal to the the magnetic field, which is given by B, multiplied by the area, the closed area. And we know that we only count the magnetic field lines that are going perpendicular to the surface area. Remember that? It was perpendicular. So if we're talking about vectors, it has to be perpendicular. So the flux is going to be B multiplied by the cosine of the area, or the perpendicular element of the area. And that's going to give us a measure of the units there. The units for magnetic flux, we've got the Weber and the Maxwell. The Weber and the Maxwell are the international units are the Webers. The Webers, because the Weber was one of the leading scientists, physicists, I think that. By the way, this is one of the things that I at least find interesting about electricity and magnetism as an area of physics, and I think I mentioned this before, that in most other areas of physics, we have to deal with the international system and the metric system and the imperial system. So it's feet and meters, or pounds and kilograms, etc. And none of you notice that in electricity and magnetism, we don't care where you come from. It's volts, amperes, coulombs. We don't care. But somebody thought about doing something. So why is this different? Weber's is the unit in the international systems. Maxwell is also units in the international system. But the difference between the Webers and the Maxwells is that the Webers in the international system, we're talking about kilograms, meters, and seconds. So those are the units. Kilograms is the reference. Meters is a reference. The only difference with Maxwell, CGS means centimeters, grams, and seconds. It just means that a Maxwell is a Weber, but divided by the corresponding 100. Okay, but it's still in international units. Okay. And I think that was just because somebody wanted to give Weber some units and somebody wanted to give Maxwell some units, and I always hope
the one is for smaller stuff.
Yeah, one is for just to reference a small for a smaller. I hope someday there's a legacy where there are units called solstice or something probably. Hopefully.
You should discover a new source of energy.
I'm so busy and tired. I don't have time.
Or like material.
A new element of gasosa.
It would probably, the units of SOSA would probably be units of anger management, I think. Somebody recently told me, I don't know, what was it, talking to somebody, and they said, they have a thing here at CEPIS that it's like, te pones sosita. And somebody was, we were talking about our children. And I was showing pictures of my daughter and my son, and they were happy. And I'm like, no, wait a minute. There are times when they get sosita. And this person was telling me, oh, you know that they call me that? A certain person calls me that. And I'm sorry about that. Why do they call you that? It's like, because this person tells me, you always want things, you're very micromanaging. You always want things to be on time. If somebody doesn't answer you on time, you get angry, et cetera, et cetera. And you're kind of like a sosita. And I'm like, well, that's the way things should be, right? If I send an email, I expect it to be answered on time. If I want things done, I want them to be done correctly. Et cetera, et cetera. So the SOSA units would probably be anger management units in an international system or something like that. This is something more that you guys identified. Will probably identify better, but the units that are used for a magnetic field are called Teslas. So the measurement of the strength of a magnetic field is called a Tesla. And obviously this is in honor of Nikola Tesla. Nikola Tesla was a very interesting character. And again, if you saw the Prestige, it's played by David Bowie. I think it's a very interesting performance by David Bowie. But Nikola Tesla was a very interesting individual. He was a very eccentric individual as well. And there's this feud between him and Thomas Edison. Whenever we think about electricity and light bulbs and illumination and all that, and a lot of breakthroughs that have to do with electrical things, we think about Thomas Edison. He's the father of the light bulb. He's the father of modern electricity, etc. But there was this feud between Edison and Tesla that some say that Tesla discovered all of these things before, but Edison was able to market things better. And Tesla was so eccentric that his eccentricities made him kind of like an outcast. And so that's why we know more about Thomas Edison than Nikola Tesla. I would argue, and this is just my theory, if Elon Musk wouldn't have named his company Tesla, I don't think we would have the name Tesla so in our minds. If you think about it, we know Tesla because Tesla, Elon Musk, electric cars, etc. But if the company Tesla didn't exist, like when I was younger, then you probably knew about Nikola Tesla because you studied a little bit about electricity and magnetism, and you know that his units were used for magnetic fields. But he wasn't that famous. I don't know if Elon Musk called it Tesla and sort of an honor to him or something like that, but at least we know the name. So whenever we're talking about a magnetic field, the units we're going to be using is are Teslas in honor of Nikola Tesla. Okay, so before we wrap it up, we're going to be talking. Well, let's talk a little bit about. We mentioned that there's a lot of laws in this unit because there was a lot of physicists that did a lot of experiments with regards to magnetism. These folks have a lot of time on their hands and were very competitive amongst themselves doing research. And so Orsted did some experiments having to do with these wires and these conductors, and came up with some interesting things. And let's look at a couple of videos of what he found out. And moment. So,
In 1820, Danish physicist and chemist Hans Christian Ørsted was setting up materials for a lecture. His materials included an early kind of battery called a voltaic pile, constructed of copper and zinc plates in a dilute acid solution, and a wire held in place here by a set of clamps.
to move this because I can't see the. So just
Ørsted and other scientists
to give a context, what's going to be shown here is one of Ørsted's experiments. And it has to do with this alignment that happens with magnetism. So the first thing he did is that he needed a battery, but he couldn't go to Walmart and buy a Duracell battery because these didn't exist back then. So how do we create a battery? Remember that we can generate or we can create energy in different ways. So we can create energy with electrochemical reaction. So basically the way we create a battery is that we can have these metal plates here. It's kind of like capacitors, kind of like an array of capacitors. And we can have an electrochemical substance here. And that's going to generate a small voltage. That's what we can use as a battery. That's what they're explaining there. Basically what's going to be done in the experiment they're going to show here is that when we connect that battery to a certain conducting material and we have sorts of poles, we're going to see that the poles are going to align depending on the flow of the current, and this has to do with the magnetic field. It's kind of like the concept of the compass. So in the Middle Ages, or when this science hadn't come up, again, we had these wizards that suddenly got a rock and said, if I put the rock in water, it's going to orient itself towards the North Pole. That's cool. Well, how can I do that artificially without having a magnetic without having a material that's naturally magnetic? How can I recreate that sort of compass artificially using electromagnetic phenomena? And that's what basically Ørsted did.
Scientists of his day knew that when a wire was connected between the positive and negative terminals of a battery, electricity would flow through that wire. Electrons actually move from negative to positive. However, the convention is to think of electrical currents as moving from positive to negative. So that's how we'll show it here, using red particles. Back then, scientists still had much to learn about electricity. Preparing for his lecture, Ørsted made a very important discovery about the phenomenon, quite accidentally. Among Ørsted's
So actually what happened is that Ørsted, let's say that I'm Ørsted and I'm teaching a class to you guys, and I want to show you that electrical current can go through a conductor. So I prepare my experiment and I put it here, and I'm going to show you that if I connect the battery, there's going to be electrical current flow. And suddenly I notice that I have a compass near the table. And suddenly when I connect everything, I notice that the compass starts moving. And it's like, oh, wait a minute, this is interesting. This isn't what I was trying to demonstrate. But suddenly, what does this mean? If I disconnect the battery, the compass goes normal. But if I connect the battery, the compass is going to start moving. What does that tell me? Somehow I'm generating a magnetic field here, and I didn't know I was generating. So that's kind of what happened with Ørsted. He was preparing this experiment for a class, and this happened.
scientific paraphernalia was a compass. Its needle, of course, pointed north in alignment with the Earth's magnetic field.
Yeah, you're doing an experiment that you expect certain results, and
Ørsted happened to place the compass near his battery and was startled to notice that the compass needle moved. As Ørsted deduced, this happened because the wire produced a magnetic field around it when it carried a current. If there is no current in the wire, the needle reverts to the alignment with the Earth's magnetic field. As it turns out, an electric current, made up of moving charged particles, produces a magnetic field that circles around the moving current, as shown by these blue lines. If you reverse the direction of the current, then the magnetic field around the wire moves in the opposite direction, and the needle on the compass flips to reflect the change in field. If you move the compass to a new spot near the wire, the needle will realign with the direction of the magnetic field in that particular location. Ørsted's accidental discovery was solid evidence that electricity and magnetism were related phenomena. The announcement of his findings incited a tremendous outbreak of research in the nascent field of electromagnetics in the early 1820s.
before another food commercial comes on. So that's one of the phenomenons that happened.
I'm delighted that you're interested in investigating the subject of.
This episode is supported by Prudential. So it's Friday, April 21st, 1820. A physics professor in Denmark named Hans Christian Ørsted is in the middle of a lecture and he's using a compass and an electric wire for a demonstration. He turns on the current that runs through the wire and he notices that the needle in the compass starts to move. And when he turns the current off, the needle moves back to where it was. Then he runs the current through the wire in the opposite direction and sees the needle move the other way. What Ørsted demonstrated that day was a fundamental discovery, the connection between electricity and magnetism. And it changed the field of physics forever. The relationship between electricity and magnetism not only explains what Ørsted and his students witnessed in 1820, it also makes possible much of the technology that's used today, from hydroelectric dams to your smartphone. It even explains why Earth's magnetic field is essentially keeping you from being cooked alive right now. And all you really need to understand the basics of magnetism and electricity is this. You're probably familiar with the basics of magnets already. They have a north and south pole. Two of the same pole will repel each other, while opposites attract. Only certain materials, especially those that contain iron, can be magnets. It depends on their molecular properties. And other metals, including cobalt, nickel and iron, are attracted to magnets, even though they aren't magnets themselves, like the metal in your refrigerator door. And there's a magnetic field around Earth, which is why you can use a compass to figure out which way is north. The magnet in the compass aligns itself with the Earth's magnetic field. Just as we use electric field lines to represent the electric field created by charges, we can draw magnetic field lines to represent magnetic fields created by magnets. And as with electric fields, the more crowded the lines are, the stronger the magnetic field. The lines point from the North Pole to the South Pole, like how electric field lines point from the positive to the negative charge. But there's a key difference. You can have an electric field spreading outward from a single electric charge, but that can't happen with magnets because you can't isolate one magnetic pole. If you chop a bar magnet in half, you don't end up with one north magnet and one south magnet. You end up with two magnets, each with its own north pole and south pole. This means that the magnetic field lines surrounding a magnet always form closed loops. We measure magnetic fields using a unit called the Tesla, which is 1 Newton per ampere meter, and 1 Tesla is a very strong magnetic field. The fields from some of the strongest superconducting magnets in the world are only 10 Teslas. Now, when Ørsted was doing a demonstration on that fateful day in 1820, he was using a regular compass magnet. But when he brought the magnet close to a wire carrying a current, the magnetic field from the current exerted a force on the needle, moving it to point in a different direction. Ørsted had discovered one of the fundamental principles of electromagnetism. An electric current produces a magnetic field. After a few more months of experimenting, Ørsted figured out that when a current runs through a wire, the magnetic field that it produces surrounds the wire. Expressed with field lines, the magnetic field would appear as circles with the wire at their center. If the current was coming straight towards you, the field lines would be pointing counterclockwise. And we use the vector B to represent the magnetic field.
Now, one thing that's important here, and this is positive here, but this is why when we're using any sort of wiring, notice that for example, whenever you see a wire, it's always covered. If we were to cut this and look inside, we would notice that there's a lot of layers of covering within it, and some of them is in some cases there's like sort of like oil inside. In others, there's things that seem like strands of hair. There's plastic. That's insulating material that the wires have. The insulating material that any cable is going to have has many purposes. Obviously, one of the purposes is for us not to touch it, because if anything touches the conducting material, it's going to conduct as well. So that's one of the purposes of isolating. The other, in some cases, or most cases, also have to do with certain elements in the environment. We don't want this to get wet. We don't want humidity to affect it, etc. But one of the other reasons for isolating, or for insulating, rather insulating, is that any electrical energy that's going through this cable is going to automatically generate a magnetic field. So any electricity is going to generate a magnetic field. So if I have a lot of cables, and these cables are very close to each other, their magnetic fields would interact. And there's one principle, it's very interesting in electricity and magnetism. And I think we mentioned this with a few examples. We mentioned it with electrical current. We mentioned that the concept of a short circuit. So electrical current is the movement of electrons, of charges. But movement generates heat, right? And heat is also going to generate vibration or movement in the atoms, okay? So movement generates heat, heat is going to generate movement, and that's what's going to generate eventually that something is going to stop working, or that's what generates an electrical circuit. The same thing happens with magnetic fields. We already mentioned that a current going through a conductor generates a magnetic field, right? And that's something that should be a take. That's going to be a question in the exam. A current generates a magnetic field, but the other thing happens as well, or the opposing effect. If I have one wire that's generating a magnetic field, and I put another wire close to it that has no voltage, there's going to be a current induced in the other wire. So the principle applies both ways. A magnetic field generates, a current generates a magnetic field, but a magnetic field can induce a current. And that's why cables should be isolated. That's why we see that when any cables that we're connected to.
Can it use the current?
Yeah. So current. So always and mostly we see this in magnetism phenomenon, electromagnetic phenomenon. Phenomenon A generates phenomenon B, but phenomenon B can induce phenomenon A. So electrical current can create a magnetic field, but a magnetic field can create an electrical current as well. We're going to see it in both ways. The general principle in physics is, and in magnetism, is this: phenomenon A creates phenomenon B, but phenomenon B can induce phenomenon A. Okay? And the example of that is that a current can generate a magnetic field, but a magnetic field can also induce a current.
That's what you say. Explain to me the example.
I can ask. I can ask in the exam for you to. We haven't gotten to that topic yet, but what I was talking about has to do with generators and motors. So I can ask you to explain a little bit about a generator and a motor, and you can use that that as an analogy or an example. Okay. I'll see you guys on